Good afternoon, ladies and gentlemen. My name is Dr. John Belkowitz. I'm excited to bring you another wonderful presentation. This time we're going to be looking at, does concrete bleed? And we're taking this from a contractor's perspective. And it's all about what we see in front of this lovely photo of a concrete surface just scaling right off. And let's just dive into the meat of this presentation. I have the privilege, nay, the pleasure of giving you this overview. Next slide. Why do we care is where we're going to start. What we want to make sure we get on the job site, what we lead up to on not only on Friday afternoon, 4:30 as we head home, but also 7 days and 7 years later, and how that concrete bleed water impacts that. And there's a negative and positive connotation to that. We ran an experiment. We went over the meaning of that bleed water. We even do an example looking at a job site and how that bleed water can be used as a benefit. And then, of course, we go into the bad side of it, the flip side of the coin, the other way the pendulum swings, and deal with that issue. Next slide. Okay, so why do we care? Let's get into it. We're going back to that first image. And what we see here is a concrete driveway in the great state of Colorado, the Rocky Mountain state. And this is somewhere around 3 to 5 days after the slab was poured. And you can see that that top surface, what is that, 1/4 of an inch, is just peeling off that top surface. And basically what we had is the concrete was setting up quickly. There was some bleed water. The finisher went ahead and waited till that bleed water came to the surface. Finished bit backed into the concrete, created a cap that hardened up because of the heat of the day. And then, of course, we had a significant amount of bleed water that came right after that, creating that delaminating layer. And then the next few days later, we have that cracking, that flaking, and the destruction of that first line of defense, that top surface. So what caused this? What is concrete bleed water? And the way I'm going to break this down, next slide, is I'm going to define it first using American Concrete Institute CT 2018 concrete terminology defined. How does it work? We've got a rudimentary illustration, and it's rudimentary. Then I go into this good versus the bad, because there is a misnomer that all bleed water is bad, and that's just not the case. Now, we're going to get into where does it come from, and then we'll finish it off with how to prevent it in a certain way. We're really going to focus that on part 2. Okay, let's get into this next slide. So the American Concrete Institute Concrete Terminology 2018 defines concrete bleeding as the autogenous flow, and when autogenous means coming from within, of mixing water within or its emergence from a newly placed cementitious mixture, what we call concrete, caused by the settling of solid materials within the mass. So the misnomer is that, when we get bleed water, it's water migrating to the surface, and it's just the opposite. It's everything else migrating down, and the emergence of that water from everything else consolidating down. The translation of this definition is when concrete sits for a long time, extra water gets squeezed to the surface. Now, we're not getting into whether or not this is a good thing or bad thing. We're just trying to define it. Next slide. Now, these next 7 slides creates that rudimentary concept. Now, this is not to scale, and I'm taking a lot of liberties in my artistic design here, but here we start off with our concrete cross-section. Let's say we take a slab, 4-inch thick slab, we cut it right down the middle, and we look into the slab. We see this gray stuff that we call concrete. We're calling that our composite: cement, sand, water, and rock. And then we have these localized sites of water. And as time progresses, as everything else consolidates down, that water starts collecting in channels and ports. It starts getting squeezed to the surface, and some of that water that was meant for curing later on, that design water, is now mechanically being squeezed up as everything consolidates down into a group form. until finally we get this pooling and puddling of at the surface and an overall change in volume of our concrete composite, with this congestion of water that was water of convenience, water that we used to get that creamy and dreamy, the concrete coming down the chute consolidated. But the unfortunate reality, it can be detrimental if it gets excessive. Now, we go from this bleeding to what does bleed water do to the concrete, the good and the bad. And again, what I showed you before is that migration of water to the surface by the consolidation of heavier materials, so that autogenous flow of water to the surface. Now, the good part of it comes from, next slide, please, overcoming evaporation. And if we define evaporation, it's the inevitable job site reality that whether you're interior or exterior, let's say we're exterior here, we have solar radiation from the sun, we have that ambient breeze or maybe a gust of wind or that sustained wind at 25 to 40 miles an hour that's going over the surface. And what that does is it deprives the water that was intended for hydration and convenience from the surface. It deprives us of that. It compromises what we had put on paper, what we had practiced in our good concrete practices, and it creates this, next slide please, bony and dry surface that if we try to put too much work into it, we'll start tearing that surface open, and worst case scenario, we'll start creating the environment for these plastic shrinkage cracks. And the ideal scenario is this, that next slide, that creamy and dreamy, that gliding over the surface, that cream that just makes that surface not only look good, but it creates that cap, that first line of defense. And the bleed water that was once in the concrete can be used to sustain this creamy and dreamy if used the right way. Now, here we go. Here's an experiment that we ran, and it's pretty exciting to look at. So let's kick off this video. And here Brooke is weighing out the material, and you can run this experiment at home. You can run this experiment whether you're using a mortar mixer. Here we're using our bucket mixer, and go ahead and run it through. Create, use ASTMC 232, the bleeding setup that they've gotten there. Either modify, use the 5-gallon bucket or whatever their size. I believe it's a 12-inch diameter. It has to be so tall, but modify it to a certain degree. Modify it based on the size of the aggregate, and to the point that you can start looking at that bleed water over time. So this is what we've got here is 2 concrete mixes. We did a Portland cement only, and then we did a replacement of our Portland cement by 20% of a Class F fly ash, ultimately reducing that hydraulic mechanism that will consume that water and more often than not create that stickiness that creates a viscosity that's going to reduce that autogenous flow of water to the surface. And over a 1-hour period, over 1 square feet, we found 1 square foot, excuse me, we found that with that straight Portland cement mixture, we got only 25 mils of bleed water. And over 1 hour with our 20% Class F fly ash replacement, we're reducing that hydraulic component. We had an increase in bleed water. And this is something that we normally see out in the field. And if we don't take care of it, it can be detrimental. So when I say the good, how can we use this? So this is a chart that's available from Portland Cement Concrete Pavement at iowadot.gov. This was last uploaded 2009, and it's theoretical rate of evaporation. What you do with this chart is you determine what your rate of evaporation of water is from your surface, so that either you can start using a membrane forming curing compound, or if you have the wherewithal, you can start creating a concrete that has a certain bleed rate that overcomes this rate of evaporation. And I want to take you through this next slide. So this is the good. This is example number one. So our example number one is overcoming the evaporation rate. So I've got this day, and it's a classic day that I have in the summer here in Colorado for 1.5 to 2.5, maybe 3 months at the most. I have an 85-degree ambient temperature with a 40% relative humidity. My concrete coming down the chute is about 80 degrees, and I got a 25-mile-an-hour sustained wind. Now, my evaporation rate we're going to find is going to be somewhere around 2.75 pounds per square foot per hour, similar to what we did, but we did it in milliliters. Now, the problem with this is, or what we see, the good, if we can overcome this, we can overcome that drying and shrinking at the surface. That water that we're going to see is going to replenish the evaporation of the water that is lost due to evaporation. Okay, next slide. So we start out with our air temperature right over here at the bottom at 85 degrees, and we go up to our relative humidity of the day. And you can see there's that 40%. And we take that over to our plastic concrete temperature, which I told you was 80 degrees Fahrenheit. And finally, we drive this line down to our wind velocity, which is 25 miles an hour. And here we see we have a little bit less than 0.3 cubic feet. I think we had a number wrong in there. I'll try to go ahead and change that. We have a little bit under 0.3 pounds per square foot per hour of water loss. Now, if we look at ours, what did we say? Ours was 25 mils. When it comes to mils, that's the same thing as grams. So if we assume that's 25 grams divided by 453.6 grams per pound, that means our bleed rate is 0.06 pounds per square foot. So we would have to create a concrete that has a bleed rate that's effectively, let's just assume that's 0.3, 5 times our current bleed rate to overcome the evaporation. And if we don't, we start running into those problems that we were talking about, the drying, the shrinkage, the cracking, the spalling, the flaking. Okay, so the next thing is the bad. The bad is when we have too much water for our bleed rate. Like right now, we're deficient. We either have to put an evaporation retarder or a membrane-forming curing compound or increase the amount of water to reduce the negative impact of that evaporation rate. But if we have the same mix but a very, very low evaporation rate, that water is not going to be used for anything. It's just going to sit at the surface. And then, of course, we have those bleed channels that bleed water and that surface-subsurface deterioration, dilution, and breakdown. And it just creates a concrete that isn't stronger and lasts longer. So now we have this example. We have too much bleed water. We have 60-degree Fahrenheit temperature ambient, 40% relative humidity, 70-degree concrete, only 5 miles an hour. Our evaporation rate we're going to see is, what is that, 1/3 of what we were shooting for. And with that, we can get all the issues if that water is not being used. So we start out with our 60-degree temperature. We kick it up to our same 40% relative humidity. Our concrete temperature is much, much lower. And of course, our miles per hour is at the low end of the scale. So if we had created that same mix to overcome that evaporation at 0.3 pounds, you can see where the problem would rise. Now we have all this water at the surface that is not being used, and we have that dilution because of standing water and that breakdown of not only our surface, but our subsurface. Okay, so this is what our bleed channels look like at the surface after everything has, I hate to use the word dried, you can use cured. But remember, those bleed channels, if we don't create that first line of defense, that top cap in our surface and our subsurface, then we're going to invite more aggressive materials to migrate into the body of our concrete through these bleed channels. Next slide. Now, overcoming the bad, next slide, means stopping this from happening. You know, we do need bleed water to a certain degree, especially if we're of one of those companies, those districts, or those states that doesn't like membrane-forming curing compounds. We've got to figure out a way how to control the amount of bleed water that's coming to the surface, or we're going to run into problems like this, where not only does that look bad, you know, and you can ask the question, and I'm sure a lot of you will make the statement, this doesn't really jeopardize the structural integrity of the concrete slab. And I won't disagree. No one is going to die from this concrete slab. That being said, the resale value of the house might be depreciated because of the aesthetic value, or in this case, the lack of aesthetic value that this concrete slab brings to the house. And no joke, the folks who own this had to sell this a few months down the road. But more importantly, if you are in a city where tax dollars are being spent to make concrete infrastructure, when you run into something like this and you were a taxpayer contributing to this, your tax dollars are not being used effectively and wisely. You know, the term civil engineer means an engineer of the people. So the expectation is, no matter where your concrete is being put down, it should be designed in the best way possible. And using bleed water as an ally instead of an obstacle is one method. But outside of that, we have to be cognizant of, hey, if we're not going to take it into account, there is a very high likelihood that we will run into the bad. Next slide. So there are 3 easy steps to create a concrete that is more conducive to a controlled amount of water that's going to migrate through autogenous flow to the surface, slowing that down, that bleeding down, not only so we can control how the concrete responds to evaporation, but also reducing the size of our pores, and then, of course, the impact that more deleterious materials will have at the later ages. Now, part 2 of this is going to be, how do we use colloidal silica, nanosilica, to change the viscosity of concrete admixtures. We'll get into a few others. You know, we'll talk about the older school methods. After that, we're going to look at, or after that, what you want to look at is reducing the amount of excess water. You know, a lot of contractors will either bless the slab or straight up mess with the truck, putting more water as needed. If you ordered a 4-inch slump concrete, but you actually needed a 7-inch, and you start just pissing up the back of the truck, expect the concrete to have problems. The concrete wasn't designed to have that much water of excess, and because of that, because of you messing with the truck, it's going to have a negative impact. And that is going to be in the response, the manifestation of bleed water. If you need a 7-inch slump, talk to your ready-mix provider. They're the ones who make the concrete. You're the ones who use it. Yeah, it's going to cost you more money, but it's going to be a better concrete. Now, when I say that, as the contractor, and that's who I'm talking to today, you got to watch that mix for segregation. If you ordered a 4-inch slump, you expected a 4-inch slump, and it comes to the job site at an 8-inch, and you start seeing some segregation, some bubbling or rock dropping out of the concrete, you need to fucking get that truck rejected. Hopefully you've got somebody on the job site taking slumps. You can't just do the finger in the air, oh, it seems like a 7, I ordered a 4. You need a third party or a certified individual to test that slump and say, hey, I ordered a 7. It was tested per the ASTMs. This is no longer a homogeneous mix. And not only does it show it in the slump, but I'm also seeing segregation. And if you're seeing segregation while it's gray concrete coming down the chute, while you're pulling your slump, more than likely, it's going to lead to something like bleeding and maybe even overdosage. But that wasn't something, overdosage of your high range. But that's not something that we were going to cover today. Okay, so hopefully you learned something. I went through a lot And listen, there's a lot of information out there that we have on our YouTube channel that not only that what is recycled concrete aggregate, but we also got some great videos that talk about concrete segregation, overcoming it, talk about bleeding. I mean, we're going to get into a lot more information on this. I'm excited to show you all of it. But in the interim, take some time, check it out. Let us know your thoughts. Thanks again for joining us. Have a great day. Go concrete! Beat asphalt.